my hexapod has come a long way. Don't let this seemingly positive progress I've made over the past couple of years fool you. There's plenty of places where Unit 0 is in desperate need of improvement. The issues with Unit 0 started back when the system was still running on SG90s, chosen exclusively because they were the cheapest servo motors I could find. Unsurprisingly, the SG90 version of Unit 0 struggled under its own weight, let alone under the weight of the battery pack and the controller board I had planned for it. To fight against doom staring me in the face, I did what anyone would do, and bought the next cheapest motors I could find, making sure they had a metal gear train. The motors I landed on, the CS929MGs, were about twice the rated torque of the SG90s, and I bought them with a whole barrel full of worms which I had no idea that I was about to break into. The motors were 2mm larger than the SG90s, a small difference, but large enough that I had to redesign the whole robot chassis from scratch. This chassis redesign resulted in wobbly leg joints thanks to my eyebrow-raising mechanical ability. Not good eyebrow raising, I mean like, oh my god, I didn't realise it was possible to screw up this badly, eyebrow raising. I usually try to avoid including fasteners and 3D printed parts because I like making my life difficult. But this time, I swallowed my pride and included screw-on link retention plates to try and solve the problem. Unit 0 also has purebred dog levels of hip issues. Firstly, the plastic joints on these parts are too thin and kept breaking. Sorted this out with some simple bulking out. Second, the potentiometer shaft in the servo motors kept breaking, likely due to the machine being designed so that there was the greatest turning moment possible applied to the servo output. To fix this, I have modelled hip support components to try to provide some support to the hip. While laying out the first combined circuit board for Unit 0, I couldn't shake this nagging feeling of, I have no idea what I'm doing. Like, I had enough of an idea to see that I'm doing things, and on the small scale, what these things probably do, but I didn't understand what lines I shouldn't cross, or where the lines were, or that there were lines to be crossed. I did a bad layout job. Which was further not helped by making the PCB myself with a permanent marker and a janky 3D printer/CNC mashup. Realising that I was the problem, I began watching lectures and reading a book to get more brain good at layout. I've now created a new layout with as many of the lessons I've learned packed into it as possible, and I hope it works because I've dumped near £100 in getting these boards spun. Most of the issues on the layout was to do with poor management of the incredibly violent back EMF spikes and sudden current draw from the new servo motors. It used to be the case that when Unit 0 first turned on, all of the legs would move immediately. This sudden, synchronous movement would try to gulp so much current from the batteries that the supply voltage would drop below the minimum required to run the regulator. This would cause the microcontroller to shut down. A few hundred milliseconds later, the supply rail would recover, the regulators power back up, and the microcontroller shortly afterwards. And just like clockwork, the legs would all move at once, causing this embarrassing sequence of events to happen again and again. Looking at real solutions to this problem, all pointed towards board relayout, and because I didn't want all of my effort on the homemade board to go to waste, I opted to manage the issue instead, by having the legs engage in smaller groups on startup, which means not only is Unit 0 startup animation cool, it's essential, for the dumbest reason possible. Even though the big startup gulp was managed, Unit 0 is still plagued by back EMF. Back EMF, or back electromotive force, is a response that inductors, like the windings of motor cores, have to a step change in current. The voltage across an inductor is described by the equation V equals L di dt. This equation says that the faster that the current changes through an inductor, the greater the voltage across the inductor. This means that the voltage across an inductor can skyrocket above the supply rail or even drop below 0 volts in a circuit. My new, super fast, super twitchy servos produce more back EMF than my design could tolerate, resulting in the microcontrollers spontaneously resetting due to rail drops or even spikes appearing on the reset pins. This became so bad that it even led to the corruption of the microcontroller flash in more than a couple of cases. Hopefully this shit show is fixed by my new layout, and worst comes to it, I'll slap some TVS diodes on everywhere. If the new layout fixes all of these problems, I'll be sure to talk about it. Probably. Maybe. Choosing the right microcontroller for the job brings many things into question. How many peripherals does it have? How fast is it? How much memory does it have? Can it run Doom? And much more. The microcontroller I chose for Unit 0 is the Atmega 328PB because it's cheap. I know how to use it. It's got a bunch of peripherals I need. It's cheap. Whether or not this micro had enough memory was always a burning question in the back of my mind. But as I was a bit unsure of exactly how to quantify it at the beginning, I kinda had to suck it and see. Which sounds way worse now that I've said it out loud. Turns out, it was a close one. Closer than I would have really liked. The problem showed itself one day when I was trying to read a coordinate from one of the leg pose matrices on the chip. A grid of numbers, which range from around -30 to +60. The number I received was close to 65,000, and poor little Unit 0 didn't know what to do with it. What had happened was my lazy programming was taking little care of how much volatile memory the firmware was using. Though the flash usage was around 40%, which is pretty good, as soon as the chip began calculating an 8x8 array of 16-bit numbers, that volatile memory got slurped up in a hurry, and the 328's little stack overflowed. I managed to battle this issue by taking a more hardware-conserving approach to writing the firmware, and splitting some functions, such as the radio control, to a separate microcontroller. I have asked a lot of the 328PB in terms of floating point arithmetic, and I've had to use some pretty neato tricks to get all of the functions that I need out of it. But it's detailed enough that I'd prefer to talk about it in its own video, if anything. Hopefully, with the motherboard respin coming in the next few weeks, alongside all of the fixes that I've spoken about in this video, Unit 0 will be stable enough to be up-versioned to Unit 1. If it makes it, then I've got some plans to do some testing with an accelerometer board, an FPV module, and other neat bits of hardware. If I'm lucky, it will be robust enough to take on an exploration mission I've been thinking about for a few months now. Yep. Thanks for listening to me ramble about my son. Bye.